Hello, I am Anshu Dubey from Argonne National Laboratory, and I want to tell you about a half-day tutorial on testing scientific software for high-performance computing that I will be giving with Alicia Klinbex from Sandia. The material for the tutorial has been put together by Ideas Project, which is a project under US Department of Energy, Office of Science, and this is dedicated to software productivity. In the past few years, software productivity and engineering have come to be recognized as indispensable for quality computing in science. However, because this awareness is relatively new, there are very few resources available to practitioners to learn how to do it for themselves. We intend to fill this gap, or at least address this gap, in the area of software testing and verification. In order to understand the importance, here is an excerpt from a lecture that Alicia gave at Argonne Training Program on extreme scale computing recently in August.
Jeffrey Chang was a scientist, I believe a biologist, who was working on generating protein structures. He inherited some code that accidentally flipped two columns of his data set, inverting an electron density map. So he got incorrect protein structures out of this code. He didn't notice immediately and published papers based on this code 5 times, and he ended up having to retract those 5 publications. Not only did this damage his reputation, but one of those papers was cited 364 times. So 364 groups of people based their work off of his incorrect results.
There are many other examples of similar breakdown in the integrity of the scientific process because not enough testing was done during development of the code. This tutorial is aimed at projects of any size or scope that has realized the importance of verifiability and wants to build a testing regime but does not have sufficient resources or expertise to do so. We will also have a section on testing regime for codes that are undergoing the refactoring process. This tutorial should help people at any stage in their career, whether they are students or postdocs or practitioners, as long as they understand the importance of verifiability and maintainability of their code. In order to understand what to expect from the tutorial, here are a few more excerpts from the lecture that Alicia gave at the Argonne Training Program.
Now we're going to talk about some specific testing challenges that are kind of unique to the computational science and engineering field. First of all, we have floating point issues, which means that you can get different results on different platforms. And you can also get different results on different runs due to multiprocessor computation. So because the order of operations is non-deterministic in these parallel codes, you can run it twice, get slightly different results. And where this becomes an issue is that ill conditioning can magnify these small differences. So your final solution could be dramatically different if your problem is ill conditioned. And if you're testing your code saying that the solution needs to be this, it needs to converge in this many iterations, the number of iterations may be different because of that ill conditioning issue and the floating point, the different results that you got because of floating point arithmetic. Another floating point issue is that when you get two numbers that you want to compare, how do you compare them when they're floating point numbers? A lot of people do diff, meaning they do a character by character comparison of these numbers. Doing a diff on floating point numbers, not a great idea because of these floating point issues that I mentioned. In this test, I determine whether the number 8 is even or odd. If it says that 8 is even, then I say, good, the test passed. If it says that 8 is odd, then the test fails. And we're going to determine whether I have covered all the code with my test. So we compile and link with the coverage flag, run the test, collect the coverage data using lcov, and generate the HTML output using gen.html. This is what our code coverage report looks like. So this is what we see for iseven.hpp. There were 4 executable lines in that code, and we executed 3 of them. We called the function, we checked that condition, and we returned true. This other case was never, ever executed or tested. So why is software verification a separate topic? Code verification uses tests It is more than just a collection of tests. It's an entire process through which you ensure that your implementation shows the expected behavior, and that it's consistent with your model, and also that the science you're trying to do with the code can actually be done.